Okay, everyone, welcome back to the third part of the lecture where we go back again to the fixed effects model. And in particular, we want to learn about how to estimate the standard errors that we normally need in order to be able to do hypothesis testing. So for the random effects approach, we have learned how to do this. So we make all these pretty strong assumptions and we get nice standard errors estimates. Yeah, you remember this omega hat matrix. That is what we plugged in, and then the rest could be estimated easily as well. So it's pretty simple to estimate standard errors with the random effects approach. Now, as we will see with the fixed effects approach, it gets a little bit tricky. Okay, so let's take a look at this. Although in the end, we will actually find out that it's not tricky at all. Okay, so again, we have looked at the fixed effect model before, and we basically what we learned is that we can transform the data, we apply GMM, and we get consistent estimators. Yes, for instance, we look at once we pool the moment conditions that are implied by contemporaneous uncorrelatedness, we get the fixed effects estimator, and of that one, we know that it's asymptotically normal, correctly centered because it's consistent, and it has this sandwich form matrix, asymptotic variance. Again, nothing new here. We know what the D, we know what the V looks like. And we also know that because we have pooled the moment conditions, beta is just identified, and therefore D, V are all going to be square matrices. And because they have full rank, we can also invert them individually. And therefore, this thing here simplifies slightly here. Okay, now Wooldridge in chapter 10.52 proposes to use a similar idea as in the random effects approach. Yeah? So we make some more assumptions in order to simplify the asymptotic variance. And in particular, he says, let's assume that the model errors are serially uncorrelated, so that you see as long as T and S are not equal, are not the same, there is no correlation in the model errors across time periods. Moreover, we assume that the model errors are homoscedastic, so that the expectation of u squared, which coincides with the variance, conditional on the x's and alpha, is simply sigma u, does not depend on x or anything, right? It's always the same thing. Okay, so if you look in the Wooldridge chapter, you will see that he writes this in slightly more compact notation, so he uses the stacked form. So what he says is that if you look at the expectation of ui, which is like a t vector, times ui prime, which is a t vector, just like now flat, right? This gives you a t times t matrix. What we get is the identity matrix with dimension t, so kind of we only have entries on the diagonal, everything else is 0. And on the diagonal, we have the sigma u squares. Yeah? And this is the same thing as saying that we have serial uncorrelatedness and homoscedasticity. And with this assumption, we can simplify this V matrix. Yeah? So kind of if we take the expectation of this kind of stuff here, we can, by the law of iterated expectations, take another expectation conditioning on x and alpha. Yeah, so xi is of course here the stacked version that contains the x's from all time periods. And well, now we have this thing here. For that, we can use our assumption, and therefore the sigma u comes out. And this, as we've seen before, this is simply the D matrix. So therefore, under these assumptions, we see that the asymptotic variance simplifies to simply this. It's just a little bit nicer. Okay, now we can easily estimate the D matrix. Yeah? So we have that the D matrix looks like this. And the rule is wherever you see an expectation, by the analogy principle, replace the expectation, this meaning the population mean, by a sample mean. Yeah, so this is what we do here. And there you go. That's an estimator D hat. Okay, now that's easy. However, we still need an estimator for the sigma u squared. And now the problem with the fixed effects approach is that we cannot directly use the residual UIT because UIT depends here on an estimate of alpha I, and the estimate of alpha I will always be inconsistent because we have fixed T. Yeah? So we only have very few time periods with which we could estimate this alpha. Okay, so let's try something where no alpha appears. Yeah, so and this is again, we applied a similar idea as before. We look at the residuals after again using this within transformation. Yeah, so with the two dots. And yeah, so here you see there is no alpha in there. And what Woodridge then shows is that this thing here is a consistent estimator of, yeah, so this is a consistent estimator of sigma u squared is what we want. And now let's take a quick look at why this thing looks as it is. Well, I mean, if we were like having this thing here, so it can be shown that the expectation of this is t minus 1 times sigma u squared. So this is where the t minus 1 here comes from. And the minus k, that comes from a degree of freedom correction, because we have to replace this thing, which is what we want, by an estimator. Okay, yeah, so this, of course, even without this minus k, this thing would be consistent, but it would not be unbiased anymore. Yeah, so for consistency, as long as n gets very large, also without the minus k, it would be fine. But for unbiasedness, we prefer to make this degree of freedoms corrections. Okay, so this thing works. Now, there's a downside to this because we had to make all these pretty strong assumptions. So for instance, we assumed homoscedasticity. And now in an Econometrica paper that is actually not that crazy old yet, Stock and Watson, who are two very famous researchers, they have shown that without homoscedasticity, so without this, the Wooldridge estimator is biased. So what they show is that as long as t is larger than 2 and you let n go to infinity, this classic estimator converges to the correct thing. But there's plus a bias term. Yeah? So you see here they also give an explicit expression for the bias, but the important thing is that there's a factor of 1 over t minus 1 in front of this. Yeah, so that kind of shows that this will be a problem whenever we have only few time periods available. Yeah. Now, what is the idea? Once you have an explicit expression for a bias, then, well, it's very simple. Let's correct the bias. So what they do, oopsie, sorry, one direction. What they do is that they simply estimate this bias and then they use the original estimator plus, or like here, correct it with an estimator of this bias. And then they show that this new bias corrected estimator actually has nicer properties. So you see here that this thing coincides with the correct variance matrix plus an error term that looks like this, OP 1 over square root NT. And the good thing about this is that now we have an n in the denominator. That means if the panel data set has lots of individuals, which is typically the case, this estimator will be good. The other thing, the uncorrected estimator has a 1 over t here, and that only disappears as t goes to infinity and not when n goes to infinity, and that is bad. So this thing here has a bias of order like an OP 1 over t bias, and this thing here has an OP 1 over square root NT bias, and this thing is much better in like short but large panel data sets. Now, what they also show is that somewhat surprisingly, like if you have only 2 time periods, there's actually no problem with the original Wooldridge estimator. Now, still, this is nice, so we can bias correct our estimator for the standard errors. Ah, yeah, true. Maybe for some of you, it's not really clear what this OP notation means. So when I write something like this, what does that actually mean? Okay, so like this big OP notation is used for boundedness in probability. So of course here I'm just giving the definition. So we have a sequence of random variables and AN is a sequence of simply real numbers. And when we write XN is big OP AN, that means XN divided by AN is bounded in probability for large enough N. Okay, now, which means that for pick any epsilon that is bigger than 0, then there will be some constant m. It can be large, like super large. It can be 10 million, 10 bazillion, whatever you like. And there is some natural number such that the probability that the absolute value of xn divided by this sequence an, that this probability, that this random variable here is bigger than this constant m, is smaller than epsilon for every n larger than this big N here. Okay, now what does that mean? It basically means in practice one thing. If you have an estimator that for which the CLT applies, so square root of n times beta hat minus beta converges to some normal distribution, mean 0, mean whatever, and some variance. Anyway, it converges to a normal distribution. That means that this estimator will be OP 1 over, oh, there should be a square root n. Okay, I will fix that. Yeah, so why? A normal distribution is simply bounded in probability. So whatever epsilon, let's say epsilon is 0.0001. Yeah? Now, if the thing is normally distributed, you can find a very, very large m so that you're very far in the tails. And then everything that is outside the tails, the probability, the area under the curve, will be less than epsilon. You can always find such an m. So what that means is that this big OP notation is very useful in order to show, well, something is, follows, for instance, a CLT. And okay, yeah. It also says that beta hat approaches beta at rate 1 over square root n. Again, this should be an n and not a t. Okay. Now there's also this little o notation, which normally denotes convergence in probability to 0. So for instance, if I know that beta hat converges in probability to beta, meaning it's consistent, then I know beta hat minus beta is little op1. So it's the same thing. Okay, this is a little recap. Now we go back to our our standard errors. And like even after the Stock and Watson correction, the standard errors are now robust to heteroscedasticity, but they're not robust yet against serial correlation because they still assume serial correlation. Now, therefore, because serial correlation is an issue in practical applications, like popular software packages, basically Stata, so that's what people use, they report so-called clustered standard errors whenever you choose the robust option. Now, clustered standard errors, well, what is that? Let's talk a little bit about clustering. And in theory, this clustering appears because of your sampling design. Yeah, so for instance, let's say there is an educational policy and you want to learn you want to see what is the effect of this new policy on learning outcomes of children in 4th grade. So this is the example that Wooldridge has, I think chapter 20 something. Now, it is very costly to have like randomly like children all over the country. Yeah? So what you could say is that, well, we randomly sample complete classrooms. Yeah? So that gives you, that's much less costly. Now, it is kind of, it's reasonable to assume independence in between classrooms, but it's pretty unreasonable to assume independence within the classroom because each of the children, they share the same facilities, they have similar background, they have the same teacher, so there may be some sort of dependence within the classroom and independence in between classrooms. Okay. Another example, so let's say again, we have our classic, we want to see what is the effect of education on wage. And now, like, just to make clear that it's really a sampling design issue, this clustering. If you, again, just open the telephone book and you randomly sample people from there, assuming that the telephone book contains all workers in the population. There is no need to use clustering because you have no sampling, no clustered sampling. Now, of course, again, if you simply go to 100 cities you simply have a random draw from cities or villages, whatever, And then within these cities, you again independently draw some individuals. Then you will have to cluster on the city level, because again, there may be dependencies within the city level, but it's reasonable to assume independence across cities. Okay. Now, another example is that, let's say you're interested in a treatment. Yeah, some policies, some cities receive funding, some other cities don't receive additional funding. And you want to learn something about how that affects the individuals within that city. Yeah? So then you have data on the individuals, but the treatment is assigned on the city level. Therefore, you will have to cluster on the city level. Okay, finally, back to our panel data set. You can also regard individuals as clusters. So again, we assume that there is no dependence across individuals. So each individual is independently drawn from the population. But of course, if you look at a single observation and you follow that observation over time, then it's pretty likely that there is some sort of dependence, and therefore you can simply regard every individual as a single cluster. Okay, so here's the chapter in Wooldridge. So Wooldridge does some more stuff here. It's a very quick summary because we want to go back to our panel data set. And the typical cluster model looks like this. And this kind of looks familiar. You see that, well, we have an intercept. There is some variables that only vary at the cluster level. There's some variables that vary at the cluster and the individual level. Yeah, so capital G is the number of clusters, mg is the number of individuals in cluster G, little g. And yeah, so this is pretty familiar. So we have seen this before. Let's say we set mg, the number of individuals within a cluster, to t. So we have t time periods and we have n individuals. That is pretty much the balanced panel data model that we have seen many times before. Now, similar to our panel treatment, we can also assume that there is an error component structure again. Yeah, so like the model errors, new GM decomposes into some cluster-specific component and some idiosyncratic error. And of course, now it depends again very much on what sort of assumption we want to make on these model errors and on the particular components. Now, this type of assumption should also look very familiar to you. Yeah? So again, if you set this to t and you set this to n, then this should remind you of strict exogeneity, since ZG now contains the data of all individuals in a cluster, or in the panel data setting, contains the data of all time periods for a particular individual. Now, in the cluster setting, strict exogeneity is of course also a strong assumption, because implicitly it says that there are no peer effects. Yeah? So because, like, for instance, here we have individual M and individual I cannot influence the model error of individual M. Yeah? So this is what is ruled out by this kind of strict exogeneity-like assumption in clustering. However, in practice, you can still kind of include peer effects in these models. It's just that you have to kind of model those explicitly by putting them in the covariates. Okay, now with this assumption that reminds of a strict exogeneity, that implies kind of our contemporaneous uncorrelatedness, which means that the model error for individual M is uncorrelated with the axis for individual M. And this would be enough to use simply the pooled least squares estimator, which would be consistent as long as the number of clusters, not individuals now, clusters goes to infinity, while the cluster sizes does not go to infinity. So that's a classic treatment. But however, so rather recently, so again, okay, it's not, research isn't that fast. So this paper is not that old yet, in my opinion. We actually can let both the number of clusters and the cluster size go to infinity. So whenever you, in your practical application, you see something that requires clustering, both, so large number of clusters, that is a must. but you can also allow for large number of individuals within each cluster. Okay. Now, what is shown is that we have a robust standard error that looks like this. And this is actually like, it's pretty simple. It's again like this sandwich form. And here, if there was no head, this would be simply the DVD matrix that we know from GMM theory. So that would be pretty simple. Now, this estimator here of the asymptotic variance can be shown to be robust to both serial correlation, or no, it's not serial correlation because there's no time dimension here, but correlation within the cluster and to heteroscedasticity, which is nice. It's simply nice. Okay. When we assume this error component structure, okay, yeah, so that's pretty much the same thing again, yeah. So we have this cluster-specific effect here, and as we've learned also in panel data, we need to kind of make a decision now. So, for instance, if we are mainly interested in the variables that only vary at the cluster level, then we may have to assume a random effects hypothesis. So because otherwise, if we use a fixed effects, if we kind of use a fixed effects treatment, then because of this data transformation that we then have to make, this XG will be wiped out. Okay, if you are comfortable with random effects, if you can justify all the assumptions that come with it, then of course you know already how to estimate standard errors because, well, that's pretty simple with the random effects approach. Again, when you use fixed effects, then you should use the within transformation. Well, because in clusters, there's no natural ordering, there's no time component, and this will wipe out CI and, oh, sorry, this should be a G. And yeah, so that's the power of habit, putting an I index. It's CG, but it will of course also wipe out the XGs. So you should do that if you're mainly interested in the individual characteristics. Now, so if you do this, then again, you can find a robust estimator that looks pretty much similar. So now we have again the U dot notation, which is the within transformed model error with a head, which means that we simply estimate residuals using our well, fixed effects estimator. And it can be shown that this is heteroscedasticity and serial correlation robust. And well, let's take a look again at what that looks like in panels. Here we are. So again, you see that everything is stacked here. And this is really the difference. So when you, like in the previous version, we had like a sum over t here and we had the UITs. When you write it like this, that means you have all combinations like of UIS and UIT in this matrix here. Yeah? So this here will be a matrix. And in general, if you allow for serial correlation, that means in this matrix, there will be entries that are not on the diagonal. And yeah, that's pretty much it, right? So that's allowing for serial correlation. So this is the clustering, the clustered standard error when you cluster on the individual level in panel data. And Stock and Watson, again in their Econometrica paper, they show that this coincides with the matrix that you want, up to an error OP 1 over square root n. So this, like the error goes to 0 at rate 1 over square root n, which means that if you have a large n panel, this can be expected to be accurate. Now, of course, they also show that if certain assumptions are true, namely the assumptions that they use for their bias-corrected estimator, serial correlatedness, then of course their estimator is a bit better. So the stronger assumptions, the better the estimator normally. That's not too much of a surprise. However, in economics, the standard nowadays is to simply be as robust as possible. So if you have to make a choice between robustness and efficiency, economic literature says choose robustness. That's pretty clear nowadays. So the standard that is implemented is this cluster robust standard error. However, it can be rather conservative, meaning that it overstates variation, and therefore you may have problem to find significance because, well, you overestimate the actual uncertainty that is in the data. And finding a little bit more efficient procedures for computing this cluster robust estimator, for instance, through bootstrapping, this is still a topic in ongoing econometric research. So if you're interested in that, yeah, so there's still room for improvement. Okay, so that on like estimation of the errors. And now the final thing before we switch to dynamic models is the classic, the Hausmann test. So this is really a, a household name. So it's, there's Jerry Household, Jerry Hausmann from the MIT. He developed this test in 1978, and this is also a classic in the econometric literature. Again, a massive amount of citations, and it should even have many more citations because many people say, okay, we're using the Hausmann test, but they don't cite the paper. Now, why would you use this thing? Well, you want to decide, should I use a fixed or random effects approach with my panel data? Now, of course, you would love that the outcome of the test is random effects, because random effects is more efficient, first of all, and second, it allows you also to, without any problems, identify time invariant variables. The parameters related to time invariant variables. However, if the random effects assumptions are violated, then the random effects estimator is inconsistent. Yeah, so in particular, when the alpha I is correlated with the x variables, you have inconsistency, which is terrible. Okay, now Hausmann kind of derived a test that is kind of often interpreted as a test of this thing here. Yeah, so there's uncorrelatedness between the xit and the alpha I for all t. And if this is true, then the random effects estimator is more efficient, meaning that its asymptotic variance is, according to the Löwner ordering, smaller than the fixed effects variance. But under the alternative, like the two estimators diverge. Yeah? So only this thing here is consistent and this thing here is inconsistent. And now the big step in what he does in this paper is to show that if you look at the asymptotic variance of the difference of these estimators, then this turns out to be simply the difference of the asymptotic variances, which of course is in general not true. In general, you would have kind of odds like the correlations or the covariances between these two estimators here. So what that means is that he shows that in the limit, like these two estimators are uncorrelated. Yeah, so that simplifies, of course, the statistics quite a bit. Okay, now again, what is the idea? The test statistic measures the distance between, the difference of the two estimators and 0. This should actually remind you of the J-test, yeah, that uses a similar idea. So under the null, of course, they should be very close together. And it turns out that if you kind of, it's a distance measure, so that's why we have a quadratic form. So this times this divided by the asymptotic variance in order to make kind of, if you were able to take the square root of this times this, it would be standard normally distributed, multivariate, of course. And the same thing here. And therefore, this thing here converges to a chi-square distribution with k degrees of freedom, and k is the number of time-varying regressors. Well, why only the time-varying regressors? Well, because with the fixed effects estimator, the other ones you simply cannot estimate. So because our data transformation will kick them out of the model. So again, in economics, it was known as the Hausmann test. Then it came out that other people in the statistics literature did something similar. So now, if you want to be precise, call it the Durbin-Wu-Hausmann test. And while this estimator is often interpreted as kind of a test of the random effects assumption, like meaning this thing here, so that's the interpretation. Of course, if the test rejects, it does not necessarily mean that this is true. Yeah? because like the limits of the two estimators, fixed effect and random effects, they can of course also differ, not only if the x and the alpha is correlated, but if one of the x's, for instance, is endogenous, it's correlated with the model error. And another warning where you have to be careful is that Hausman uses the assumption that we made on the random effects estimator that made actually the random effects estimator so efficient under the null. And if that assumption is not true, then the asymptotic distribution here is not true anymore. And therefore, the critical values from that distribution may be off. So you have to be aware that whenever you use the Hausman test, this assumption here, that should be reasonable. Yeah. Okay. Um, yeah, that's it for standard errors and a little bit of Hausman test. And in the next part, we will go to dynamic models.